Hey guys, Bobby Thompson back with another video, and in this video we're going to talk about the macro versus the micro. And what I mean by that is we're going to compare claims and features of the heliocentric model, and we're going to see how those stack up against the flat Earth model, comparing those features in the micro. And what I mean by that is if we try to replicate what the claims of the full-size model at a smaller scale, how do those stack up? So with that said, buckle up and sit back because it's about to get weird. All right, we're going to cover 15 subjects, and those 15 subjects are what holds us together, gas pressure next to a vacuum, thrust in a vacuum, combustion in a vacuum, bodies of water, boats sailing over the curve, sunsets, northern and southern star trails, the Antarctic daytime, that was a typo there, shadows on clouds, Lake Ponchartrain, lunar eclipses, measuring the Earth, and modeling gravity. That said, before I get started, I tried to give credit to everyone. Any video I borrowed, I shared the link and gave credit to whose channel I found that. I tried to reach out to who I could. Not everyone responded. So if I've given someone credit incorrectly, just let me know. I'll update my video. I'll update my description. I will try to add all the links to the description if you want to go see those channels for yourselves. And with that, let's get started. What holds us together? So is it electrostatic attraction or is it gravitational attraction? I like to add some context so there's no ambiguity to what I mean. As far as I did a Google search, what holds an atom together? And you'll see that Google's first result says the forces of an electric nature. We should all know that. We have protons, neutrons, and electrons. These are electric components of an atom, or at least they have charges, right? So it's referred to as a chemical bond, but again, the forces of an electric nature. That said, enter Walter Lewin. Walter Lewin is a physics professor at MIT. MIT is one of the most prestigious and highly ranked academic institutions in the world, well known for their area of science and academia. And let's see what he has to say about the effects of electrostatics as compared to the effects of gravity.
And so you will easily be able to show that this ratio is roughly 10 to the 36. So the electric force is 36 orders of magnitude more potent than the gravitational attraction.
Okay, that was interesting. Electrical forces, aka electrostatics, which is what he's talking about. If you go back and watch this video, I urge you to look at the link. Again, I'll have it in the description. Go back and watch the presentation. And he's saying that it is 36 orders of magnitude stronger than gravity, or 10 to the 36 power.
And so you will easily...
All right, moving on to the next slide. What holds our world together, according to Walter Lewin?
So what holds our world together? Well, on the nuclear scale, 10 to the minus 12 centimeters, very important are the nuclear forces. On an atomic scale, up to thousands of kilometers, it's really electric forces that hold our world together. But on a much larger scale, planets and stars and the galaxy, it is gravity that holds our world together.
Okay, interesting. Gravity. So he said up to gravity works for the cosmological scale. Sorry about that. But he said it was electrostatics that held our world together up to on a scale of thousands of miles, right? He called that the atomic layer or the atomic level. So he said gravity didn't come in until at the cosmological level, which he classified as planets and stars, solar systems, galaxies, the cosmos and whatnot. So that's Walter Lewin. He's a MIT physics professor. I don't think any of this is in contention. I think this is well understood and taught, although we are tricked and deceived by what we've been taught about gravity. I think this guy probably knows what he's talking about. So I think it's safe to say, or at least it can be argued, that electrostatics hold our world together. Now let's move on to gas pressure next to a vacuum. So the claim is that in the heliocentric model, or what I call the macro, we have a pressurized Earth next to the near perfect vacuum of space. So we can't produce that. I have nothing to show you because there's no video experiment to show you because it simply can't be produced. You can't have a vacuum next to a pressurized system without a container. But we do have someone that claimed they had an answer for every flat Earth argument, and let's hear him talk about that.
I think people that first encounter flat Earth, they all say, "Well, I once believed that it was a stupid idea, but I tried to refute it and I couldn't." Well, that's because you didn't go to the right sources. You went on the internet and you heard these arguments from flat Earthers that you couldn't answer.
Yeah.
That's because you didn't know the answers. I know the answers. I haven't encountered an argument yet I couldn't refute.
Okay, so Professor Denny Faulkner, astronomer, said he hadn't encountered an argument yet he couldn't refute.
I think.
So let's see what happens when Nathan Thompson asks him about this very argument.
So how do you have gas pressure without a container? Nothing? Danny Faulkner, PhD astrophysicist, runs an observatory and profits from the lies.
All right, thank you for that, Nathan Thompson. All right, so thrust in a vacuum. There's the claim in the heliocentric model is that we have rockets and satellites and space stations and things that need adjustments to their trajectories zipping around space and using thrust in a vacuum. So that said, I've got a little experiment here. This came from Cody's lab, and what's going on here? Let's see what happens when he tries to demonstrate thrust in a vacuum.
So as you can see, which says magnetically
I'm just going to try to save us some time here.
You can see when I turn the fan on, it blows the feather all over the place. This is, of course, at atmospheric pressure right now. So I want to take this down to Martian conditions. You might have noticed the Martian reference over there. First thing I'm going to do is add a little bit of dry ice to the chamber, just so that...
All right, I'll save us a little time. He's going to vacuum out all the air.
Between 4 to 6 millimeters of mercury, which is, of course, the pressure on this thing to levitate.
They're vacuuming out the air.
If you can see the gauge over there, you can see that the air pressure is just about to the point where it would be considered the surface of Mars. So since we're at Martian air pressure, let's unplug the vacuum pump and let's turn on this fan. Place your bets as to what's going to happen to this feather. Now the fan's only going to produce maybe 10 miles per hour worth of wind. On the surface of Mars, the fastest recorded wind speed is about 70 miles an hour. But let's say the superstorm in the Martian had wind speeds of 200 miles an hour, 20 times what we have here. To compensate for that, I imagine the feather is about 20 times easier to push over than a spaceship. So let's see what happens. Okay, fans on. And the feather's not moving. In fact, let's zoom in on that.
Not the slightest disturbance to that feather.
Not even flinching. Just turn the fan off. So as you can see...
All right, so in that experiment by Cody's lab, he was unable to get a feather to move in front of a fan. So let's talk about what thrust is, right? So I went directly to the source, nasa.gov, looked up their definition of thrust. This is on several of their websites, right? I just grabbed one. They all say the same thing. Thrust is a mechanical force, so the propulsion system must be in physical contact with a working fluid. What are fluids? Well, water's a fluid. Gas is a fluid. Is a rocket in contact with a working fluid in space? I'd argue that it's not. That's not my understanding of space. I understand it's a near perfect vacuum, but there's a new argument. So the argument now is that, and let's listen to this person. I don't know if he has science writers working for him or he's just really intellect. He's saying, and I understand this argument, that it's not combustion pushing off fluid as much as it is in space, the expulsion of mass. And I get that, because if you push mass away from you, it pushes mass in another direction, which that that makes sense. If you have two people in a zero-G plane and they kick off each other, or one pushes the other, you're going to go in opposite directions. That's great. The only problem with it is it's incredibly inefficient, right? Imagine how many bowling balls I would have to propel myself around space, right? Opposed to a jetpack, right? Which might be the weight of 5 bowling balls. I can fly up to the top of Mount Everest, or what? Well, assuming certain things, but I can fly around the surface of the Earth. And I'm not stating any distance. I mean, I can fly around the circular Earth. But the claim is, again, that it's expulsion of mass. And to move, we'll talk about it after the video. So let's get into this video.
So in this case, I'm going to prove that wrong, because we're going to be able to see the propellant come out, and we're going to see if the can moves before the propellant reaches the wall. So the wall of the vacuum chamber is going to be very close, but I'm going to use my high-speed camera so that we can see at the moment the can bursts open. If the can moves forward, then that means it's obviously not because it's pushing off the wall, but the real reason is because it's throwing mass this way, and that pushes the can that way. It's the same way that rockets work.
Okay, I wanted to make sure you caught that. It's the same way that rockets work. So it's a little bit different, right? Rockets in space opposed to jets in our atmosphere or boats in water. It's not so much anymore the combustion and those forces pushing off a fluid. When you get in space, he's saying it's the expulsion of mass. That's not what we have with propellers and jet turbines. It's not the expulsion of mass. So in space, the new argument, the new claim is it's the expulsion of mass. And let's see if we can observe this expulsion of mass. I'm sure that we can.
So let's go atmosphere, slow-mo footage, and see if the can moved before the soda hit the wall.
Let's slow it down some more.
I'm toggling. The wall's clear over, toggling back and forth between frames. But the liquid is still...
All right, great. So what he's saying, what he goes in great depth to explain, again, go to the Action Lab. Now, this is from the Action Lab, not Cody's lab. It's a different place. He has stated that in space, the way rockets work is they expel mass. I know this is getting redundant, but I want to make it very clear, and we talked about it before the video and after the video. Now, this is a very misleading experiment, in my opinion, because the object you're trying to propel here is probably on the scale of 5% of the mass that's going the other direction, right? The bulk of the mass of that Sprite can are the contents, the liquid inside, right? The container is nothing more than a skin. I don't know the exact weight or the exact thickness of that aluminum, but it's certainly a far cry from the contents, the weight and the mass of that liquid inside. So yes, absolutely. He just expelled 95% of the mass to move the can, right? So, but imagine in space when you have, I have no idea, I did not look up for this, I should have. I normally like to be that prepared to know the weight and mass of the space shuttle. And what's it take to push that in one direction, right? It should take something equivalent to its weight and mass, right? Or its mass, right? It should take something equivalent to that. And what do you do when you have to turn, right? You don't have the efficiency of a combustible propellant, right? It's not like, rocket fuel in Earth atmosphere is very efficient. We know that from amateur rockets and from other examples of that. But mass, I've never seen a mass propulsion system or a mass expulsion system, right? I've never seen a car drive around a neighborhood propelling or expelling bowling balls, right? I've never seen a bowling ball propulsion system. So the reason you have it is because it would be incredibly inefficient. So again, if you want to say, if that's your argument, I think we've it's very clearly stated that NASA admitted themselves, thrust has to make contact with a fluid. The propulsion system has to have contact with a fluid. There's no contact with a fluid in a vacuum. And as admitted in this video, we're now talking about the expulsion of mass.
So in this,
let's talk about combustion in a vacuum. So at the macro level, or the heliocentric model, they're claiming that you can burn fuels in space. That's a whole separate argument from thrust in space. Can you have combustion in a vacuum? Well, we did some experiments. I didn't, but someone did at the macro level, right? We did them in a vacuum chamber, and let's see what the results are. So our first test is, can we burn paper? Now, this comes from Cody's lab. I linked to the video in this one. This is the name of the video is Fire Possible in a Vacuum. We're going to start with paper. I only clipped, for brevity's sake, the failures, which they all failed. But if you want to see what they do, what I say by the failures is when he burns them in Earth atmosphere, they burn fine or even explode. So these are to save time, for brevity's sake. We just caught them of what happens in a vacuum. So let's look at paper in a vacuum.
Okay, let's close the door, pump out the air, see what difference it makes. Now that most of the air is gone, let's shoot it with the laser again and see if it still ignites. As you can see, there is no ignition, which makes sense because I've removed almost all of the oxygen. I still see smoke though. In fact, so let's get a closer look at that. Here you go, safety first. Let's put on some laser safety goggles onto the camera so you can see it a little bit better. Okay, let's see what happened to the paper. So the paper was definitely charred by the laser. You can see it's blackened and in many cases completely burned away.
All right, so if you noticed at the beginning of the video that the paper was burning, that's because he just did a demonstration with the laser showing that you can ignite it, no problem. And it ignited, it was burning. He had to blow it out, he puts it in the vacuum, he removes all the air, and you can't ignite it. You can burn it by focusing the laser on it, but you can't ignite it. Ignition is what's required for combustion. Okay, so next video, let's move on to, now we're going to look at gunpowder. So gunpowder, obviously highly explosive in Earth's atmosphere, but in a vacuum.
Most of the air is now gone. Let's see what happens. Gunpowder did not ignite.
So for brevity's sake, I'm not going to play the videos to the end, but he can very easily ignite these through this glass. The glass is not a problem. He's done demonstrations to show that he can ignite. It's the lack of oxygen, right? That's why these. So gunpowder will not ignite.
I saw.
And let's move on to the next test.
Most of the air.
So we're going to look at rocket candy. Now we're getting more volatile in our sources. So let's see what happens when he tries to use ignite rocket candy. Rocket candy is what's used to propel amateur rockets.
No ignition. That's interesting. I did see some little poofs as it tried to burn, but it was unable to sustain itself. So even when it's in one solid piece, it can't chain. And
so rocket candy fails in a vacuum. You can't burn it. Now, what's more volatile than that? Let's move up to acetone peroxide. Yet even something more volatile. Let's see what happens.
Acetone peroxide in vacuum in 3, 2, 1. It still didn't burn.
So you can kind of burn it, but it will not ignite. You can't get ignition. You can't get combustion from it. You can only burn it if you leave the heat on it long enough, right? So that was acetone peroxide. let's move on to thermite, right? You might have heard of thermite. It's used in military to demolish buildings and whatnot, obviously highly combustible. Let's see if he can get thermite to ignite in a vacuum.
I did not get an ignition.
All right, he did not get an ignition. So
I'm going to try again.
Let me go back. So even to take that a step further, what he's going to try now is he's going to try baking out the volatiles to see if he can get So he really wants to try to get something to ignite in a vacuum. And this is his last experiment. He's taken thermite, something highly, highly volatile. And he thought, well, maybe there's volatiles inside the compound that's preventing it from igniting. So he tries baking those out with a torch before he tries to ignite it in the vacuum again. And let's see what the results of that are.
I'm going to try again with the thermite, but this time I'm going to bake out any volatiles from the iron oxide first. That way, perhaps the laser won't push the pile around quite so much. Okay, I'd say that's fairly well cooked. Let's try it out in a thermite mixture. This time it's been baked. It's inside of a vacuum. Let's see if we can get it to light. There's sparks. Oh, it's burning. It is actually burning. Oh, that is cool. It actually burned. It burned very slowly, but it actually worked.
Yeah, for the sake of combustion, for propelling something, I wouldn't, I would call that a failure, right? So he was able to, there's probably a compound we can make, but even this is a separate argument from thrust. But obviously combustion in space is a problem. You don't have oxygen. Even trying to ignite compounds that have, I forget the exact word for it, but basically like an oxygen source mixed in with it, it's still a problem. And at best, you can just kind of barely get it to burn, almost like almost something similar to wood burning.
I'm going to try.
All right, so let's move on to bodies of water, right? So the claim is that we have this spherical Earth that appears to be a perfect sphere, and we have this water bending convexly around it. And can we observe that on the micro? And the answer is no, right? This is obviously a very simple one. A lot of people like to argue it that you can, but I've been to the ocean. I live near the ocean. I've been there many times. I've been on more flights than I can count. I've never seen curvature. And Neil deGrasse Tyson will even tell you that you can't even see curvature from twice the height of the Felix Baumgartner jump if you subscribe to him as a priest. But this is what we see, right? No curve at the at the micro. Here we have Salar de Uyuni, which are salt flats in southwest Bolivia. And this is the largest salt flat in the world, coming in at nearly 4,250 square miles. And when it rains, the surface is so perfectly flat that just a thin coating of rain, which you can walk around, you can drive around, ride your bike around. There's all kinds of videos showing this. There's just a perfect mirror on the ground. And look, you can't even see the tires sinking into the water at all. It almost looks like it's parked on a mirror, right? All right, and this little photo. This is obviously water when you can see through the clouds. But again, when we send up high altitude weather balloons over the ocean, as long as it's not a fisheye lens, we always see the horizon rising to eye level, and it's always a flat plane across the x-axis. So in summary of that is at the micro level. We cannot see water convexing, and at the only place we theoretically can observe that is at the cosmological scale, if you believe in the heliocentric model. But let's talk about boats sailing over the curve. So this is one that's argued about quite a bit, and the claim is that a boat disappears hull first as it goes over the horizon. And here's an experiment from Rob Skiba's channel.
I'm in.
And go.
That's a trip.
Ship going over the curve and the sun setting.
Perfect. And that's on a level.
On a flat table.
You show me, pull it back. Do me a favor, just pull it back like without. That's the table. There you are.
So to explain that, to clarify what you're seeing is Rob came up with the idea of putting and I'm not sure if he was the first, but he came up with the idea of putting a lens in front of the ship to simulate Earth's atmosphere, right? Because we have water in our atmosphere. We know that. It's called humidity, amongst other factors. But that water refracts light, and it acts as a lens. So we call that Atmos lensing. You may, if you're a heliocentric model believer, call it atmospheric lensing, but I'll choose to call it Atmos lensing.
I'm in.
So on the micro, boats sailing over the curve, we're able to disprove that that's due to the curve of the Earth, right? So that works fine as far as that. That's a perfectly acceptable explanation. I can't understand why anyone would think that it's not. And to take that a step further, there are many, many videos out there where people with like P900 and P1000 cameras are able to bring ships that have sailed over the curve back into focus and bring them in. But let's move on to sunsets. So the claim is that at the macro level, that the sun is setting behind the geometric horizon, and we see the sun get obscured by the Earth. And same technology, same person, Rob Skiba, who's no longer with us. Thank you for this video, brother. But he's, again, the argument still stands, and it's still a subject, is people will argue him separately. They'll say, oh, we see ships sail over the horizon, and we see sunsets over the horizon. So let's see what happens when he uses this apparatus on a sunset. Obviously, you're going to see the same thing.
Here's what I came up with. I've got my magnifying sheet frame, and I created a little stand to paste the sun on it and keep it the same height over the flat surface of a table. So the sun is always going to be parallel with the surface. And check this out. All right, here's the first test of a sun moving over a flat surface, and with no atmospheric magnification, it does what we might expect it would. It gets smaller as it goes away from us. All right, now let's see what happens when we add in our atmospheric magnification. Again, water and refraction. Water causes magnification and refraction, right? So let's bring the sun back. Oh, check this out. Refraction bends the light downward. It made the sun set on a parallel surface. As it was moving parallel, the same height, the whole way over a flat surface, the refraction caused the sun to set. Not only that, well, let's bring in the beginning of that little test, and we see that it maintained pretty much the same size, too. Pretty close. And of course, that's because as it's moving away, the magnification is still taking place. And so even though the sun's further away than it was in the beginning of the test, the magnification basically preserved the same size, and the refraction made it set. Now, I'm just going to put forward a crazy idea for you to think about. And that is, if Rob Skiba could figure this out, I'm just going to go out on a limb here. I think it's quite possible that the creator of the cosmos could have figured out the same thing and engineered our beautiful sunsets, thanks to all that water he placed in our atmosphere.
All right, thank you, Rob, for that. I think at the micro level, sunsets are sufficiently explained. There's a perfectly valid explanation. You may not like it because it doesn't agree with the heliocentric model, but it's perfectly valid. The Atmos acts as a lens, which it should. It has water in it, and to take that a step further, there's plenty of videos of times when it's not very humid. The humidity is very low. There's very little water in the air, and there's a very small temperature difference between the ground and the Atmos, which minimizes refraction. And we've seen the sun disappear into the sky. It just got smaller and smaller and smaller until it just vanished. So that's just more evidence. So I think at the micro level, the flat Earth sufficiently passes that test. Let's move on to the northern star trails. And again, the claim is with the northern star trails is that the stars are so unbelievably far away that they don't move, right? And that's a valid argument. Parallax, you can observe that in trees, that the farther and farther and farther something away it is, it's so far away you can't see it move. But that's one thing when you're just driving by something. But when you're spinning at all angles through space, I think that's very hard to believe. I don't think that can be produced. I don't think there's an experiment on Earth where you can have, as a matter of fact, I'm absolutely certain no one can do the experiment where I have a room with dots on all the walls and I spin a ball and put a camera on it and then take that ball in every possible angle in an orbit. And those stars always create perfectly concentric star trails, right? And they're going to say, well, your room's not big enough. I get it. My point is you can't reproduce it on Earth. You can't. So the claim on the macro fails. It fails because it can't be reproduced on the micro. So this is a case of the heliocentric model making a positive claim where it can't be reproduced on the micro. And here's an example of those star trails. When we focus on the pole star Polaris in the northern hemisphere, we get these perfectly concentric star trails, which on the micro, this is just the firmament. This is the firmament spinning, and this has been observed many times. I didn't even think to put a video of that in. It would have been, that's obviously very easy to comprehend though. If we have a dome over us and the stars are affixed in that crystalline dome, when you turn that dome and you did a time lapse of that, you would get star trails. But that leads us to the next argument, because as you pan to the equator and more south, the lines go from concentric circles in the north to straight lines at the equator to concentric circles in the south. And globe Earth proponents will use this as an argument, and they'll say, oh, the stars why are they rotating in a separate direction on the northern and southern hemispheres? And they're not. No matter which direction you look, north or south, the stars are still going east to west. That's not up for debate. It's indisputable. You're just changing, you're turning around, right? So when you're seeing something go from right to left on the sky and you turn around, it's now going from left to right. That's a fact, right? So they use both of these arguments, and it's pretty funny to me. So the next argument is that, even if you get past that, you can't produce star trails, right? How do you have concentric circles in the south? That would be understandable if the Earth were a globe or a sphere and spinning, and you had a southern pole star. But let's move on to that. Let's compare the macro to the micro. So here we have what Good Times for All. I don't know his name, but I do know his channel. And this, I would call this he calls it a hemispherical lens, which I like that. I'm going to adopt this terminology. And he goes on to show you that you can have all of the constellations revolving perfectly, just as we observe them in real life or stellarium, projected on this sphere. And we can also observe the counter-rotating star trails produced by this hemispherical lens, and we can produce the southern star trails. Okay, so I'm going to skip around a little bit. It's a long video. For brevity's sake, I'm going to try to shorten it up, but let's go through it.
like this. So all the constellations, even when you get down way down in there and look to the side, so all the stars you could see, you'd be able to see from that point of view, from the center of that sphere, hemispherical lens. So we create a hemispherical lens by how, just on the distance that it doesn't, it wouldn't make sense.
Sorry about that. Somehow, all right, didn't mean to do that.
It wouldn't make sense in the square. Now, as you can see, we can get it to make the two different rotations. You see the clockwise and the counterclockwise. See that there?
So those dots are representing stars, right? So they're representing stars, and as they pass, the hemispherical lens is creating this counter-rotating effect.
Now, if it were a hemispherical lens, we would see that our eyes were creating a bunch of circles. Now, when you have a single dot, watch what I can get this single dot to do. You can get it, look at that. And it even curls around both edges, kind of.
So I would say, and this is a great video, I highly recommend watching it. It's very easy to find on Good Times for All's channel. Go check it out. But I would say that is a more than sufficient explanation. It does create everything that we see. So I'd say that's a pass at the micro level. But now let's look at the Antarctic again. This was a brain fart when I was putting together the slide. I was kind of typing up all my subjects real quick and never went back and cleaned this up. But at the Antarctic daytime, right? So the claim is on the heliocentric model, you'd have to have 24 hours of sun, right? Not just sunlight, but 24 hours of sun as we observe in the northern hemisphere. There are thousands, potentially even millions, but certainly thousands, if not tens of thousands of videos on YouTube and different video sharing platforms of the Arctic 24-hour sun, which happens 3 months a year. Well, there should be 3 months a year in the southern hemisphere where we can observe 24 hours of sun, but do we? We do not. We get daylight for 24 hours, and that's not being disputed, but you want to see an explanation for 24 hours of daylight. So let's check this out. So you can go to time and date, or there's plenty of places. You can see it on certain maps. It's annotated. You can, throughout the year, this is what the sun, how it would have to change, how the lighting of the sun would have to change on a flat Earth. The sun's light, look, at some points in times, it wraps around and almost touches itself or creates a twilight on the opposite side, right? So how could you do that, right? People think that the light underneath the sun would just create a small local circle, and without the firmament, that would be the case, right? But once you add in the firmament, right, like this crystalline dome that reflects, because domes do reflect, wow, now we have the colors of the sunrise and sunset are explained, but what about the shapes of the light, right? Because this is what's in contention. This is the argument that they say can't work on a flat Earth. But it works perfectly, right? Again, this hemispherical lens would give us these light patterns. And this is from David Weiss's DITRH channel, which again, I think everyone knows who DITRH and David Weiss is. He has this Flat Earth, Sun, Moon, Zodiac Clock app, which you can download on your phone. But am I an expert on refraction? No, I'm not an expert. Am I an expert on lensing or lenses? No. Do I craft lenses or make them? No. But does this look like it is a potential explanation? Yeah. A lens can create this effect. So how could you prove that it's not? You can't. You can't prove that it's not. A firmament, I think that's very convincing evidence that a firmament dome, a crystalline dome, would reflect and refract light to give us these shapes that we observe, that we would have to observe on a flat Earth in order for it to work. So I think that's a pass. I think it works. What about shadows on clouds? Because this is one that's in all the debates now, is all the globe Earth proponents bring up Mount Rainier. And I'm going to try to give credit to everyone where I found all this information. If you're not a fan of Taboo Conspiracy, you're missing out, because he always finds an answer for everything, and he does the best experiments, in my opinion, although there's plenty of people doing experiments. But Taboo Conspiracy, Ben with them, is out there doing work. I borrowed this shot from one of his videos. Hope he doesn't mind. But this is Mount Rainier, and this is the shadow that globe proponents argue that the sun must be lower than the cloud deck to cast its shadow on the bottom of the cloud deck. And that is, when I first saw that, I was like, wow, there has to be some explanation, right? And let's just look at, now this is from P-Brane, another great flat earther with a great channel. Again, I can't give enough props. Go out there and check him out. This video came from him. And this is a time lapse of a shadow on a mountain. And it's extending out. And what we believe that shadow is you're seeing that projected on the bottom. And we can go further. We're going to dissect this further and prove that's actually what it is. This came from Taboo Conspiracy. I believe this is Ben's graphic or his illustration. I hope he doesn't mind me using it, but if he does, I'll take it down. I will add a link to his video. I'm giving credit for it here. I'm trying to drive traffic to his website and not trying to take credit. So thank you if you do allow me to use it. Thank you very much, Ben. So that said, obviously not to scale. We understand that, but the effects still stand. Here we have the sun, we have the earth, we have the geometric horizon of the sun as witness of the earth as witnessed from the angle of the sun, and we have the mountain, Mount Rainier, and it's blocking, Mount Rainier is blocking the sun's rays, and it's casting a shadow on the bottom of the cloud. That is their argument, and they demanded an explanation because that is absolutely what they said was causing it, and they demanded an explanation, right? So that's what that is. But what about every time there's not a mountain, right? When the Earth's spinning, the sun's spinning, and as it's spinning away from the sun and the geometric horizon, it starts to eclipse the sun's shadow, as it did with Mount Rainier. Why don't we see the shadow created by the Earth appear on the bottom of the clouds? Why don't we see that, right? Why don't we see this? Because that makes perfect sense. If globe earthers came on, if globe earth proponents like McToon and all these people come on and laughed at flat earthers, and they did, and said, give us an explanation, you would expect this exactly. Where is this? You owe us this now. This is now something everyone who has taken that argument of Mount Rainier's shadow now owes us this. This debunks your model. That's what I say. I say, if you don't see that, you don't have eyes to see. You were never meant to see this, and there's no arguing with you. This is truth. This is objective truth, not subjective. This is objective. All right, that said, let's move on. 1 second. This is a great video. I mistyped this here. I think Globy McGlobeface is the Globe Earth proponent, and I think Jason with TikTok, Jason347, is the one who showed this thorough debunk. And I apologize for that, but let's just go ahead and get through this.
Let's see these forced results. Under your parameters, of course.
The long triangular shadow cast by the sun on the mountain on the bottom of the clouds is only possible on a globe.
Looks pretty flat and level to me.
You can only get this shadow if the sun is below the mountain and below the clouds, shining upward.
Definitely is not pointing up. Definitely above that mountain clouds.
You could have figured this out in 10 seconds if you just tried it yourself.
Alright, Clover McGlobe face. Here we go. Got our cloud deck. The box. We got our mountain. And we have our sun that is above the cloud deck. Completely above. Drag the sun back parallel, not dropping below the horizon. What do we have? A triangle shadow. Check this out. Alright. First play just now on those quarters. Dang, long triangle. Shadow right there. Of this truck, about 6 feet high. I'm sorry, 5 feet high. I will show you measurements. Say the light is definitely just under 6 foot high. You know what? I can probably go higher. I could probably go on top of this truck, to be honest with you. Let's see. Got an idea. Probably not.
All right, for the sake of brevity, we won't watch the whole thing. Jason 347, thank you, because this has been debunked. Now Mount Rainier has been debunked in 2 separate ways. Number one, if the Earth were a sphere, we would see the geometric horizon eclipsing the sun's rays, and we would get a shadow as a result of that on the bottom of the clouds. We don't see that. And number two, he just basically did it to scale. So he did it from above the cloud deck and then put it on the top of a vehicle and did it again. I mean, this is, I don't know how much higher you have to go, but I would say that's a perfectly acceptable explanation. What's not an acceptable explanation is why we don't see a shadow on the bottom of clouds from the Earth eclipsing the sun as it spins away. So you owe us that, Globe Earth components. Let me know when you get it. Feel free to send it to me. I'll be looking out for that. And now let's look at Lake Ponchartrain. So on the, again, what I call the macro, which is the actual power lines going across the Lake Ponchartrain, they appear to curve down at the end. The pylons disappear. But do we see that on the micro? We do. We see the same thing. The bottom of these cans disappear. Now, if this were one person doing that, but here's another experiment. Do these people just all have curved floors? Here's another experiment on a table. Do they have curved tables? Is it what people are buying curved tables at their houses now? Here's another experiment on a different floor, all different people. And the legs of the army men are getting chopped off. And if you don't believe that, well, here's putting the camera on the floor from 20 feet away. And here's a close-up, and you can see that the legs are being eclipsed. It's just how angular resolution works. So if none of that is enough for you, under the right conditions, you can actually see the towers. Someone else, Michael Kramer, went out and kept trying until he got it, and they will go according to perspective, the way we would expect it to go, right? As there's no sign of curve in this photograph he was able to take. So I think Lake Ponchartrain passes the micro examination, and let's move on to lunar eclipses. So the claim is, on a lunar eclipse, the Earth is casting a shadow on the moon as it eclipses the sun. And let's hear Bill Nye talk about it.
But every now and then cast a shadow on the moon. And when it did, that shadow was always round. Now the only shape we know of that always casts a round shadow is a...
Okay, so why is that misleading, right? Why is his little video misleading here? It's because he's using a flat moon, right? Why didn't you use a spherical moon? Because it'll create a problem. What someone would see, he was accurate with in the demonstration saying, well, we're going to use a spherical object. Yes, the spherical object will create a spherical shadow, but if you cast that shadow onto a spherical object, now you've got a problem. So let's move on to, this is from the Potter's Clay, another great channel I highly recommend visiting, but let's see what happens. I don't know his name, I'm sorry, but he's going to do some experiments casting a shadow from a spherical object onto a sphere.
Here I have a ball, and I'm going to cast the shadow of this ball onto another ball. All right? Look carefully at the shape of that shadow. Now here's the shadow of a ball being cast onto a plate. And please take notice of how the shadow is different here. Here's the shadow on a ball. Shadow on the plate. Now here is a picture of a lunar eclipse. I don't know about you, but I think this presents a problem for the globe Earth model.
I agree with you, sir. This is a problem for the globe Earth model, right? So the problem about casting a shadow or any image on a ball is that it distorts, right?
Here I have a
and I wanted to see this at a different scale to kind of even see it exaggerated more. It took me a little bit. I did many experiments with different size balls from different distances until I was able to cast a shadow of the same size. I was able to get the distances to where this shadow cast a shadow on this ball that was the same size as it eclipsed, okay? But watch how the shadow goes from a small circle to a large circle. You'll see this, and that's because you're casting on a sphere, not a flat surface, right? And that sphere is going to distort the shadow. So when the shadow, the circle is growing in size, okay? Again, this was an experiment I did, but at the end, it's just the same size. But look over here, it's getting smaller. I don't know if you can see, but if right there, that's the outline of a smaller circle. If we were to continue that circle around, it would not be as big as the ball that's being cast on is, until it eclipses the whole thing. Again, you'll see it turn into a smaller ball as it kind of exits the side. Now, if you're having trouble following that logic, imagine projecting your face onto the wall, onto a flat surface, right? No problem, your face is going to look normal. But what if you project your face, a photo of your face using a projector onto a sphere, right? It's going to be distorted. It's not going to look like you, right? It's going to look like someone else. Like you have gigantism or something. I don't know. But so that's the problem. And here we have, let's look at this video. We have a lunar eclipse from May 15th to 16th in 2022. So this wasn't too long ago, less than a year. And let's see if this circle is distorted at all. This is the shadow of the Earth being cast on the moon. Let's see if there's any distortion of that circle at all. None whatsoever. It's like it's being cast on a flat surface. And this is from APOD videos. And this is, even though it's an interesting graphic, these are actual photos that they've kind of, to demonstrate the moon moving through the umbra of the Earth. This is all to scale. The umbra's to scale, the moon's to scale. And what you see is there's no distortion. Again, I just want to drive this point home. There is absolutely no distortion of this circle, the umbra of the Earth, right? So on a sphere, that would change, which you can go back and look. It absolutely would. Look at the two videos. I don't know how much more proof you need. If you dismiss those videos, on what grounds? On what grounds are you dismissing them? If you say you don't see it, well, I have to disagree with you. So in my opinion, on the micro, the heliocentric model's explanation fails. On the macro. On the micro, it's excuse me, I think it stands. And now let's move on to measuring the Earth, okay? So the claim is on the macro that Eratosthenes was able to in real life, in actual scale, was able to measure the Earth. And I want to add some context to this first, because our terms need to be well understood if we're going to go into this subject. Is light divergent? That's the first thing we need to know. Light emitted from a bulb, a candle, or a lighthouse are examples of divergent light. Light is by nature divergent. Scroll down a little bit more in the Google search. That was the top result. Let's look at the next one. This is a beam. Is sun a divergent beam of light? Examples are the sun. Lamps, bulbs produce divergent light, right? So if you're not familiar with the light inverse square law, you can read about it. Here you can read it. I believe this is from Petapixel, the inverse square law. And it says that a subject area decreases inversely proportional to the square of A's distance to the energy for source. Here's a better. It works as follows. If you double the distance between a subject and a light source, it illuminates a surface area 4 times greater than the one before. So every time you double the distance, it illuminates 4 times greater the object. And we can see that in the next slide. Oops. 1 meter to 2 meters, look at how much more surface. And that, again, just the law, which the inverse square law is just that. It is a law of nature, is that as light moves forward, it diverges. Otherwise, it wouldn't be a law, okay? That's taught in physics. So light is naturally divergent. And this is just a graphic illustration of what we observe when we look at a light source. And this is an actual photograph. This is called a fog something. This is like kind of looking at a light source when it's foggy, but just kind of goes to drive the point. And again, anytime you look at the sun, you'll observe these crepuscular rays, which all end at the sun. Granted, this is a combination of perspective and converging if going towards the sun, or diverging coming at you. And so I consider Eratosthenes, some people call him Aristophanes, I call him Eratosthenes, and I hear that pronounced differently in other ways too, but most commonly Eratosthenes. He presupposed parallel rays. I don't know why you would. We've never observed parallel rays. This is all if you believe in Eratosthenes, by the way. It's very easy to back someone into history if you control the teachings of history. But why would someone thousands of years ago believe in parallel rays? Have you ever seen parallel rays come from the sun? I've only seen crepuscular rays. I've only seen divergent rays. Also, they say, the claim is that Eratosthenes measured accurately a 24,900 circumference Earth. But if we go down to the micro level, which I consider flat Earth micro in comparison to the heliocentric model, because we have a very small sun and a very local sun, the math works the same way, right? We get this, it works just fine on a flat Earth. So hypothesis 1, flat Earth, would be a small close sun with divergent rays, which is what we observe and how we know light works. Hypothesis 2 would be a large distant sun with parallel rays, which light doesn't work like that. And we have no reason to believe it does. We've never observed that. And we don't know why they would presuppose something like that thousands of years ago. But if you don't believe it from me, if you're still hesitant, there's a great YouTube channel called Vsauce, and he's got 18 million subscribers. 18 million. That might be the largest YouTube channel I've ever seen. And it's a science channel. I don't think you get to be that big of a science channel spewing bunk science, right? He probably got the math right. I don't think he's out there spreading misinformation. So let's see what Vsauce had to say about it.
The same phenomenon Eratosthenes measured could be explained by a flat Earth if the sun were only a few thousand miles away and 32 miles across. The math would work out the same.
So Vsauce is saying the math would work out the same. It would work. So does a small local sun and work as far as for Eratosthenes proof? Again, this is always thrown out as definitive proof. I'll hear people say Eratosthenes proved the Earth was a sphere thousands of years ago. Did he? He made some ridiculous presuppositions. But here we have Vsauce saying it works perfectly fine on a flat Earth, which I agree with. All right, so modeling gravity. This is my last thing, my last subject. And what I mean by that is gravity on the macro scale, which to me would be the cosmological scale, would be what we observe in the solar system and beyond. Does it work? And does it work on the micro scale? Well, the micro scale here, how can we model gravity on a small scale? You can't, right? We heard Walter Lewin with MIT say that gravity doesn't even work at the atomic level up to thousands of miles. It's all electrostatics. If that's the case, the only thing we can do is use mathematics and shrink it down into a program, right? So we can run simulations. That's the only way to shrink it down if we don't have a spare galaxy. So that's the only way we can test gravity. So my comparison for what we supposedly observe with our solar system versus what we observe when we plug it into a simulation, which is my version of the micro. So let's look at the three-body problem. What is it? Well, this is one of, you can look it up anywhere, just type three-body problem, and I just grabbed the top thing that came up, which was the University of Oregon. The problem of determining the motion of three celestial bodies moving under no influence other than that of their mutual gravitation. No general solution of this problem, or the more general problem involving more than three bodies, is possible. No solution is possible. This is current teachings. To this day, there is no solution. It is unsolvable. So what does that mean? What are they talking about? Well, if you go to physics channels, and this is just one I grabbed off of YouTube. This one was called Physics Simulations. If you use the mathematics that support gravity and you take those equations and you build them into a simulation, and you run that simulation, even with just the moment you go above two bodies, it breaks almost instantly. They just swing out of control. So we have this mathematical formula that everyone swears by. We were all taught to worship it, called gravity. But Newtonian gravity was already replaced, or Einsteinian gravity. And Einsteinian gravity has time dilation and objects shrinking as they speed up, and it has warping and bending space-time, and it has dark energy and dark matter, which we don't even understand, which makes up 95% of it. So for me, this is just bunk science. If you can't make three bodies work with your model's broken. Our model works fine. How you all are the ones claiming it's all these bodies in our solar system with moons going around them and well over two bodies, and that doesn't work. So here is this is a astronomy museum, the largest astronomy museum in the world. This is in Shanghai, China. And it was inspired by the classic three-body problem. So it pays tribute to this three-body problem. I mean, this is a pretty big problem, right? And you know, let's hear it from someone else. This is PBS. Let's hear what he says, how he defines the three-body problem. Now, this came up at the top of the search results. It was in like the top 3 or 4 or 5. Let's hear how he explains the three-body problem.
Despite the beauty of Newton's equations, they lead to a simple solution for planetary motion in only one case, when two and only two bodies orbit each other, sans any other gravitational influence in the universe. Add just one more body, and in most cases, all motion becomes fundamentally chaotic. There exists no simple solution. This is the three-body problem.
There exists no simple solution, right? There's no solution. It's not a simple solution. And
despite the beauty of Newton's equations,
it gets funnier as you go, right? This was a long video, and I think they did that intentionally. I clipped it down to make this is just a small fraction of the video. And I want to preface this before we go a little bit deeper. So I was, you know, I have a friend of mine that's very intellect, and we've been discussing flat Earth versus heliocentric model for actually several years now. And he is always the globe Earth proponent. And when I came up with when I presented him with the three-body problem, he just shot back this video and said, there's many ingenious solutions to it. But that's it. He didn't watch the video. He just sent me the video. And I watched the video and I sent it back to him and I said, hey man, it doesn't fix it. And he just said, yes, it does. He goes, in many ways, yes, it does. And many people, the moment they see a credible organization, you know, what we consider to be credible, we just take it at face value. It just says there's solutions, right? And then this person, like many other people, I guess makes the assumption that I'm not intelligent enough to understand what they're saying, right? They're talking physics stuff, astrophysicist stuff. They figured it out. If they say they figured it out, they figured it out, because the title of this thing talked about how they figured out the three-body problem. So let's see how he figured it out.
Famous for being impossible to solve.
Wait a minute. We got to watch this video. I'll skip this one.
The three-body problem is famous for being impossible to solve. But actually, it's been solved many times and in ingenious ways.
Really? You don't say. So the three-body problem is famous for being impossible to solve. But in actuality, it's been solved in many ingenious ways. Ingenious. Mind you, this is some strong verbiage coming from this guy. It's been figured out many ways, and they're ingenious. Oh, let's check out some of these ingenious ways. Let's just start with the solution one. You'd think solution one would be a big one, right? You'd think that'd be the one that just crushes it. Let's look at solution one.
How do we do it? Well, just because the three-body problem for the most part has no useful analytic solution, approximate solutions can be found. For example, if the bodies are far enough apart, then we can approximate a many-body system as a series of two-body systems. For example, each planet of our solar system can be thought of as a separate two-body system with the Sun. That gives you a series of simple elliptical orbits, like those predicted by Kepler. but those orbits eventually shift due to the interactions between the planets.
Whoa, absolutely ingenious. We're going to treat them. We're going to take however many bodies there are, and we're going to break them. We're going to ignore the fact that there's multiple bodies, and we're just going to treat them all as two-body problems, and we're just going to combine them all together. But they inevitably break. Of course they do, because there's no solution to the three-body problem. So this is a solution. The solution is we take a solar system and we just act like it's a whole bunch of two-body systems, but then it doesn't work, but that's a solution, right? Listen to the end again.
Shift due to the by Kepler, but those orbits eventually shift due to the interactions between the planets.
Right, yeah, there's not a solution. You didn't fix it, but if you just look at them as two bodies, you're ignoring the effects of the gravity from the other bodies. You can't do that, right? That doesn't work.
How do we do it?
That's hilarious. Okay, but let's look at solution 2. This one's arguably better.
Another useful approximation is when one of the three bodies has a very low mass compared to the other two. We can ignore the minuscule gravitational influence of the smaller body and assume that it moves within the completely solvable two-body orbits of its larger companions. We call this the reduced three-body problem. It works very well for tiny things like artificial satellites around the Earth. It can also be used to approximate the orbits of the Moon relative to the Earth and the Sun, or the Earth relative to the Sun and Jupiter. These approximate solutions are useful, but ultimately fail to predict perfectly. Even the smallest planetary bodies have some mass, and the solar system as a whole has many massive constituents. The Sun, Jupiter, and Saturn alone are automatically a three-body system with no analytic solution.
Honesty, he's telling you right there at the end, a little bit of honesty. There is no solution, right? I think this is hilarious. If it's three bodies, so his solution was that if it's three bodies and one body is very small, like a satellite, we're just going to ignore it. So we're going to do the math like it's a two-body problem. Again, this is the ingenious solution. We're just going to treat it like a two-body problem, but that didn't work because everything has mass and eventually it breaks, right? Of course. So again, still no solution, hence why it's considered impossible, and hence why there's a astronomy museum dedicated to it, and hence why it's still taught in all the schools that it's impossible. But this guy called it this is the second ingenious, right? Einstein would have come up with this. Hey, let's just, as long as the third body is so insignificant that we can just ignore its mass, we'll just use the two-body solution again. Ingenious. Let's look at number 3. This is the most fallacious one right here. This is the most misleading and scientific double talk probably of all.
To get an accurate prediction for most three-body systems, you need to break the motion of the system into many pieces and solve them one at a time. A sufficiently small section of any gravitational trajectory can be approximated with an exact analytic solution. Perhaps a straight line or a segment of a two-body path around the center of mass of the entire system, assuming everything else stays fixed. If you break up the problem into tiny enough path segments or time steps, then the small motions of all bodies in the system can be updated step by step.
So what he said was, if we break it into little tiny pieces, we can do the calculations on this one and say this is going here, but this is separate, and we can say, well, this one and this one are pulling, so this one will go here. But then you got to stop, and you got to recalculate it, right? So you got to go to the next step.
Sufficiently small.
And then you got to so here's the point. You have to do that linearly. You can't predict out. It breaks, right? It's not a solution. He's saying you got to do them in time steps, and you have to do it for a second, and then you got to start over. But you can't just run this out, right? You can't go, because if you do, again, there is no solution. They admitted that in the very beginning. But this is the ingenious solution: is that we can make a prediction, compare it, correct it, make a prediction, compare it, correct it. This is what he's saying. Okay, so let's move on to the next ingenious solution.
To get an accurate prediction for most three-body systems. Yeah. The first was Leonhard Euler, who found a family of solutions for three bodies orbiting around a mutual center of mass, where all bodies remain in a straight line, essentially in permanent eclipse.
Okay, so did you see that? So this is ingenious solution number 4, is as long as it's a 3-body system and they're in perfect line, essentially always in an eclipse, all you're doing is making this one body. You're just combining these masses and making it a 2-body system. Yeah, it's a 3-body system, but no, it's not. It's 2. Technically it's 3, but it's not. It's 2. So also, how is this a solution? How do you apply this to our solar system? How do you use it in a model, right? It only works in this model, right? You can't apply that to our solar system. There's still no solution for our solar system. You still can't fix the 3-body problem unless you remove all but 3 bodies and make two of them together and make one eclipse the third one at all times, right? This is hilarious. So another ingenious solution. Let's look at solution number 5. This has to be the one. This has to be the one that... This has to be the ingenious ones.
Joseph Louis Lagrange found solutions in which the 3 bodies form an equilateral triangle. In fact, for any 2 bodies orbiting each other, the Euler and Lagrange solutions define 5 additional orbits for a 3rd body that can be described with simple equations. These are the only perfectly analytical solutions to the 3-body problem that exist.
The only perfectly, you heard it, this is the only perfectly analytical solution. All the other ones led to approximations. All the approximations were wrong. They all broke. So this is the only one that works. Well, if you have the luxury of designing your own solar system, that's a great luxury, by the way. Absolutely ingenious. I do like to design solar systems, so thank you for this one. I'm working on one now out in the Alpha Centauri area. But what I'm going to do with that is I planned on using a spoke pattern with 5, an equilateral triangle. So this will work out just fine for my solar system. Wish we could apply it to our solar system. That'd be great. But thanks for the information. So that was the 5th and final, absolutely ingenious way they solved the 3-body problem. They turned it into a 5-body problem with equilateral parts. They made it a wheel, and as long as you're exactly at those places, that's great. So we just go around and rearrange solar systems and flick out little planets whenever they're inconvenient.
Joseph Louis Lagrange.
So, in summary, I'm sure I made some mistakes. I'm a little older today. My brain isn't what it is. A lot of times when I look back over my old videos, I'll say things like 4 million Earths fit in the sun, or I've made some mistakes when I know what the real answer is, and my brain just kind of glitches out. But I'll leave out words, so you have to excuse me for that. And I've just made some mistakes, right? I'm not perfect. This isn't a science book. I'm free talking. I'm not reading off a script, so. A lot of times I'm going to say things that are wrong. I know I'm going to take a lot of slack for it. It's not easy making these videos. If you want to know what I meant, or if I meant to say something on purpose, then ask me. Because a lot of times we say things incorrectly. If you've ever spoken in public or made these videos, if you've done them yourself, you'll see that people get tripped up from time to time. So that said, I try to give everyone credit I can. Hopefully nobody has a problem. We'll see if I get any copyrights when I upload this. Hopefully if someone does see I'm using their content, they won't strike me. They'll just ask me to take it down. And if so, I'll just re-edit the video without their stuff. I will have a ton of resources in the description. I will have links to all of these videos. I hope you enjoyed the video. Thanks for watching. Until next time, take care.